Welcome and hello. This is a video exercise in HEC HMS, and in this exercise, we're going to be dealing with gridded precipitation method. This is a meteorological method for precipitation. We're going to use a gridded precipitation a grid for precipitation as well as temperature, and then compare the total runoff volume without evapotranspiration and then later with evapotranspiration. So that's what we're doing in this exercise. I'm going to go ahead and leave the link to the instructions right here that I have on the page. So check out the video description. That's where I'll put the link. You can just find it in the HEC HMS tutorials and guides website under meteorologic models for historical precipitation, gridded precipitation method. Okay. So the first thing we want to do here is download the files, this gridded.zip zip file. Click download and then wait for that to download. Okay, that's almost downloaded. And okay, we're done. Here is the zip file over here on my desktop. Then I'll just go ahead and close that. The first thing we want to do is get the files out of the zip file. It's called gridded and then punx, punks. So here are the files for our project inside the punks directory. So I'm going to go up one level. Now I want to go ahead and put those files into this directory here. So wherever you want to unzip this punks directory project, go ahead and do that and then let it run. And then once that's copied or unzipped, you can go ahead and delete the zip file. All right, so we have this project directory right here. Let's go ahead and open HMS and then open and then navigate to that punks project folder. Open, and then punks, open, and then it's going to be this .hms file here. So go ahead and hit select. All right, looks like I have a bunch of data already loaded up, including two different basin models. There's May 96 and September 2018. We're going to ignore the 96 data and only work with the September 2018 data for this exercise. So here we have a watershed with a single subbasin and a sink, which we have data for over here. Also, we have some gridded data. There's precipitation grid set and a temperature grid set. If I expand over here in the Watershed Explorer, you can see that data is right here. Here is the actual path. It's a single DSS record, and then here's the file name and the path name. So out of curiosity, I'm just going to go ahead and check this out. It's in data and then precip.dss with the path of just precipitation for part C. And then our temperature grid is right here, and it is its own DSS file right here, temp.dss, and temperature is the only path name for part C. So I'm opening up DSS view right now. I'm going to navigate to those two DSS files here, and then data, and then can I open both at once? No, okay. Precip.dss first, I suppose. And then after that, temp.dss, which is for precipitation and temperature. Here's the precipitation. So what we have is hourly data that starts at basically the beginning of September 2018, and then it goes all the way to the end of the month. So 720 records, 721. So let's go ahead and take a look at this. This is gridded data, remember. So now let's highlight the first one, look at the metadata. So it's a very small grid. It's just 16 by 15. The cell size is 2,000, which I believe is 2,000 kilometers on each side. Period cumulative, and the units are in millimeters. Okay, so this is just 1 hour of data. If I want to look at the data, here it is. It's all zeros because it's all green. But if I highlight the whole data set and then click on that graph button, I can toggle through the 721 different records. And eventually I should hit a record that has some non-zero data. Like right here, we have precipitation 3.7 millimeters for that cell for that hour. So that's kind of how the grid data works. All right, we could do the same thing for the temperature as well. I assume it's the same coordinate system. And yeah, that looks familiar. Oh, actually, 15 by 14. 1 second. This is 16 by 15. Okay, a little bit different, but 703, 1055. 1 second. 704, 1055. Okay, so there's overlap. I think there's just one extra row or column on the precipitation. Okay, it looks good. If we want to actually look at the temperature data in a grid like we did for precipitation, then here it is. So we can just toggle through. And then if we hover, we got 20 degrees Celsius. Let's see. So Pennsylvania in September. Yeah, I suppose it's Celsius. Looks good. So I'm going to close DSS. We can actually get back to HMS now. I brought this up because I like to do everything myself, and some of these exercises basically does all the work for you and only lets you do one little thing. So what I want to do is just take a step back, remove these data sets and add them back in as if we created them ourselves or if we had downloaded the data ourselves. There is a little discussion here about the gridded data. Gridded precipitation data is generated using gauge data, radar data, and satellite data. The quality and availability of this sort of data is only getting better with time. And here's a link here to a number of different gridded data sources in the table with links here on the far right. And I have not looked at these data sets myself, so go ahead and check them out yourselves. But that's just a reference here within the introduction. But what it tells us to do here on the steps, I'm going to go ahead and narrate the steps as I do the demonstration. So here's step 3. This is talking about the grid data. And then step 4 is the meteorologic model. We'll get to that in just a moment. What I wanted to do is delete this data, and then I'll delete the temperature grid as well. So now we have no grid data. Some of this data is superfluous, like the time series data. We're not going to use that. The terrain data, that's already been loaded up and used, so we don't need to deal with that either. So let's go ahead and add that grid data back in. So grid data manager. What we want to do is add the precipitation grid and the temperature grid. So one here and then one here. We'll start with the precipitation grid. So I'll go ahead and select new. For the name, I'm going to just use the same name that was there previously. And then for the temperature grid, I'm going to click new and then give it this name and create and then close that. So now in our grid data, we have our precipitation grid set, one of those, and one temperature grid set. Let's go ahead and make that assignment as if we just created the DSS file on our own. And by going ahead and selecting the precipitation grid set, now in the components editor, it's going to be single record DSS. The DSS file is going to be that precip.dss. So let's go ahead and navigate to that. It's right there. Let me just double check I'm in the right directory. No, I'm not. Boom, data, and then precip.dss. Okay. And then for the path name, we'll click on this report button here, and it should show us the different paths. So part C, precipitation, is what we want for all of the hours of the month of September 2018. So I'm just going to go ahead and select the first one and then click set path name. What it's given me is precipitation in part C, but then it's only given me this first hour here. So I'm going to delete that. And then I have to add one slash, I believe. Yeah, so it's slash, slash, slash. Precipitation is my part C, followed by 4 more slashes, just delineating parts D, E, and F. Let's go ahead and do the same thing for our temperature. So I'll click temperature, and then single record DSS is what I want. I'm going to navigate to that DSS file, which is right here, temp. Let me double check. Yes, this is correct. And then data, and then temp.dss. Temp is short for temperature. And then I'll click this icon here, select temperature, the first record, click set path name. And just as I did with the precipitation, I'm just going to make it general, and I believe it would just grab all the temperature grids. Well, we'll see if that works later. I'm going to go ahead and hit save. Next, the instructions on step 4 tell us to create a meteorologic model. So go components. We can actually just go create component meteorologic model this way. Or another way to do it is go components and then meteorologic model manager and then click new. It's the same thing. From here, we notice that we already have a MET model created for that 1996 example. And that's why we have a directory up here. But we want to create a new MET model for the 2018 simulation. So let's go back, new. We're going to name that meteorologic model September 2018 gridded and create. So we have our new model there, and it should show up right here. That looks good. Down in the components editor, we have all of our different components and methods associated with that meteorologic model. First thing we want to do here is change this precipitation to gridded precipitation, which is right there. And also make sure that the unit system is US customary, which it is already. The next thing we need to do, this is step 9 now, is click on the gridded precipitation icon here underneath our meteorologic model. And then for grid name, this is a required field. We need to select our precipitation grid, which is this MRMS precipitation. There's no need to perform a time shift or a transpose. This data is already cleaned up and ready to go, ready for use in HMS. Also, when using gridded data, the instructions notify the user that this subbasin is a gridded discretization. So what that means is if I go up to the basin model here and then select the Mahoning Creek subbasin, what you're seeing in the components editor for discretization method is structured right here. So you may have used none or unstructured or file specified in as a default setting or in a different project, but right now we have it set to structured. So if we do that, there is a discretization tab right here. If I select that, we can see specifically the details of that discretization. For instance, the projection is SHG. We're going to leave it like that. And then the cell size is 2000. If we want to see the discretization on the map, because I know I do, we can go up to View Map Layers. There's this layer here for discretization. So go ahead and turn that on. And we're still not seeing it, which leads me to believe I need to calculate the cell grid size. 1 second. So I'm going to go up to GIS and then compute and then grid cells. So let that run for a moment. And then there we go. We now see the grid cells, and this is based on the projection and the cell size that we selected. More information about subbasins and the discretization methods are covered in my lesson 15. I have a separate playlist for lessons. And if you select lesson 15, subbasins discretization, it goes into more detail about the discretization and the different types. All right, next up is step 10, and that is to create and run a simulation. So we're going to go up to Compute menu, Create Compute, Simulation Run. We're going to name our simulation September 2018 and then click Next. Now what we need to do is select the basin model. So for each of these steps, 1 through 4, we're just going to select the 2018 version. Here it is for the basin model. Here's the 2018 Meteorologic model, which we created. And then lastly, the control specification for 2018 September, and finish. All right, going to go ahead and click Save now. Now we see a September 2018 option for our run simulation. So let's go ahead and run that. Okay, looks like a successful run. By the way, the control specifications we have set for September 18 are right here. It's the first 16 days of September using a 1-hour time interval. So that would come into play when we look at our results. Speaking of which, let's go ahead and take a look at those results, specifically at the outlet of our subbasin. So I'm going to right click on the sink and then click Graph. What we see here is a hydrograph at the outlet for the first 16 days of September. Of course, it peaks here, which is around 85 or 8600, about 8500 CFS at the beginning of September 11th, end of September 10th. We can get the actual data if we want. Zooming in may help a little bit. So we could just zoom in on the plot here, and it looks like, yeah, just above 8500. Or if we go File, Tabulate, we can look at the data this way as well. So if I go ahead and navigate to early September 11, here is the peak value right here. It looks like it's 8516.8. Now there's no reason to do all this if we just want to know that peak value, because I can go back to the plot, right click, and then View Results, Summary Table. We now have a peak value of 8516.8, and that's CFS. We'll just round up and call it 8517. We also have a total volume here, which is currently in units of inches, but if I want it acre feet, which I prefer, is going to be 52,327.5 acre feet. Remember, that's over the course of 16 days with that storm event. The next step in the exercise is step 11. It's optional, which means I'm doing it. Add a canopy and a evapotranspiration method to our meteorologic model. Select the Mahoning Creek subbasin in the September 2018 basin model, and then in the component editor, choose the simple canopy method. So let's go and do that. Here is the subbasin meteorologic element, and then for canopy, we want to select simple canopy. Next, a canopy tab right here in the component editor appeared. So go ahead and click that. And then what we want to do for initial storage percent, according to the instructions, is say 0 will be our initial storage. Max storage will be 0.1, which appears to be in units of inches. And then the uptake method will be simple, which is this one right here. And then the other parameters we're just going to leave as they are, which is the crop coefficient of 1.0 and the evapotranspiration of only dry periods. Since this exercise includes gridded temperature data, we can include that as well. In the meteorologic model, we want to select gridded temperature. So I'm going down to my meteorologic model. Here's temperature, and then here's the method gridded temperature. Now we have a gridded temperature icon here in the meteorologic model. When we select it down here in the components editor, we have to select our temperature grid. And we will select that RTMA. That's the name of our temperature grid right here. So that's good to go. No time shift is necessary. We're also told in the instructions to change the evapotranspiration to gridded Hammond. So that means going to meteorologic model right here, and then for evapotranspiration, gridded Hammond. If I select the gridded Hammond icon, then there's a Hammond coefficient. I'm just going to leave that as it is because the instructions tell me to. The last step is step 16. This tells me to recompute the simulation and then check out the results. So let's go ahead and do a save first. And then we have September 2018 still selected and run. Okay, so it finished, it closed. Now I'm going to right click once again on the outlet and then select view results and graph. Now we have a similar shaped graph, but I can tell that we have lost about 500 CFS from the peak flow because it used to be around 8,500 and now it's around 8,000. So that's interesting. Let's go ahead and take a look at our summary data, which is in the summary table here. What we have is a peak discharge of 8,002.1 CFS. We'll just say that's 8,002. And then the volume is 44,332 acre feet. So there's a significant drop off of both peak discharge and the total volume over that 16 days from this subbasin, which does include some precipitation events after we added the canopy and the evapotranspiration method. Taking a quick look at the results, here's the first computation run with no evapotranspiration. 8,517 was our CFS, and then with the evapotranspiration, it dropped down to 8,000, so 94% of the original. What's even more interesting and a larger difference is the total volume. So the first run without any evapotranspiration, it was 52,327 acre feet. And then, as you can read on the screen, with evapotranspiration, it was 44,332, which was 84% of the original. So 8,000 CFS less over those 16 days of September 2018. Well, that was it for this exercise. We used gridded temperature data and gridded precipitation data on a subbasin that had a structured discretization, and we analyzed the results both with and without an evapotranspiration method.